All right, so we've learned how to take the derivative. Now what? What are we supposed to do? Well, one cool thing we can try is taking related rates. Now, let's imagine a little balloon, a little tiny balloon here, and the balloon is going to grow bigger. All right, so you can imagine that if we look at the volume of the balloon, 4/3 pi r cubed, you can see how there's a variable in the volume. It's the radius. And if the radius is growing over time, you can see the radius is growing over time, dr over dt, that's increasing over time, then you know that the volume is also going to be increasing over time. So this is the dv over dt. And that's basically what related rates are. Pretty easy. The next cool thing we can do is the linear approximation. So linear approximation of a tangent line. So that means we're literally going to be estimating the equation of the line. So let's say we're given y equals x squared right here, and we want to know what's the tangent line right here at, for example, a equals 2. A equals 2, and this would be Lx right here. The equation for that line, we can actually approximate it like this. Lx equals f of a plus f prime of a, in parentheses, and then x minus a. This is f prime right here, f prime of a, x minus a. And if we did some math here, we started plugging the numbers, we would get Lx equals, if we plug in f of a, so a in there, it would be 4, right? 4, and then plus, if we take the derivative of that, it would be 2x. And then you put in the 2 into that, and you would actually get 2 times 2 is 4 again. And then over here, x minus a. A is 2, so it's just going to be x minus 2. And once we do the math, and just some little algebra here, let's just rewrite this. It would come out to 4x minus 4. Okay. And so that's going to be the equation of the line. You can see it even intersects right here. That would be negative 4 right there. So 4x minus 4. Pretty good estimation. Well, what's the point of this? Well, let's say we wanted to estimate for this particular line right here, the value of x equals 2.1 for x squared. So doing it in your head is kind of difficult. You might want to put it into a calculator. Okay, for x squared, it's pretty simple. But let's say there's a really complicated equation, right? So the line might be a little bit easier to estimate if we were to imagine just shifting up that line just by 0.1. Notice that line, it's almost like that y squared. It's not quite that y squared. We're going to get into that in the next section, how it's not quite the error of that, but it's pretty close. Let's see what the difference would be. So if we actually plug this into the calculator, we would get 4.41 for x squared. When we put 2.1 at x squared, it would be 4.41. But let's say we did the linear approximation and we didn't use a calculator and we did Lx and we put 2.1 into this formula, it would be 4. That's literally 8.4 minus 4, which is 4.4. So I can actually do that estimation in my head. I couldn't do 2.1 squared in my head. That'd be too weird. But 4.4, I can do that. See, right in my head right there. So that's kind of cool. So anyway, that's the use of linear approximation. You can actually approximate things. Notice that the error is only 0.01. That's so small. And we're going to get into the errors in the next section as well.